Welcome to my YouTube channel. I am Vasant Naik from Government First Grade College, Kumta. In this video, I am going to explain the different terms used in the special theory of relativity. This is the first session on special theory of relativity. The first term is space. Here, space is the boundless three-dimensional extent in which objects and events have relative position and direction. That is, if the object is in the any room, have to say that object is in three-dimensional space and it has a particular position and it is in particular direction. Therefore, we need the space to understand the relativity and the time. Time is the ongoing sequence of event taking place. That is, if the two objects are moving, one object is moving fast and another object is moving very slowly, then we need a time to specify its position with respect to the time. If I are saying that if the object is moving slowly with respect to what we have to decide, with respect to time we have to decide. Therefore, time is the ongoing sequence of event taking place, the space-time. Here, this term is important. Space-time is any mathematical model which fuses the three dimensions of space and the one dimension of space into a single four-dimension manifold. And the another important term is frame of reference. An event can be located with reference to some coordinate system is called the frame of reference. For example, if in the room there is an object, we have to specify its position with respect to our position, or we can specify its position with respect to its distance from the right wall, left wall, floor, or roof. We need some references, and that frame is called frame of reference. Example, we can consider the Cartesian coordinate system, polar coordinate system, or spherical coordinate system. Here the next term is event. Something that happens in space at particular point. Remember, at particular point and time is called an event. Therefore, an event is completely defined by location and time. In order to understand that, let us learn another term, the observer. The term observer as shorthand for a specific reference frame from which a set of objects or events being measured. So let us learn event and observe by using one diagram here. Here it is X, Y, and Z are the Cartesian coordinates, and this is the frame of reference. And you have to take an observer. Here is the observer who is at point O. Now this observer is at rest. Therefore, what is his location? He is at origin and he is at rest. As the time increases, he is at the point O only. Therefore, we have to locate, that is, we have to locate that particular observer. respect to its position and with respect to time also. So let us take one event here. Let us imagine that this is the person who is standing on the road. This is the car. Now the person who is the observer, remember, and the car both are at rest. And now the car is moving along the x-axis. Now we have to define this event. What is event here? We have to define it by its location, that's its position and time. What is its position? It is moving along the x-axis, and we have to observe that with respect to the observer. Therefore, as the time changes, the position also changes. That's the definition of the event. And is the observer. What is the definition of the observer? For a specific frame of reference from which a set of object or event being observed by the observer. The observer is observing this moving car. Why we need the time here? So let us take here. This is the moving car which is moving very slowly, and this is the moving car which is moving very fast. If even though both the cars moving the same distance, but the first one is moving very slowly and the second one is moving very fast. Therefore, in order to define the event, we need both location as well as the time. And this is the another frame of reference. Here both the observers and event is moving. Therefore, there is the observer is moving and the event is also moving. And the next one is frame of reference. Is classified into inertial frame of reference and non-inertial frame of reference. Let us first learn about the inertial frame of reference. A frame of reference in which Newton's first and second law holds to is called inertial frame of reference. That is, if the object continues to be in the state of rest or uniform motion, continues to be in the state of rest or uniform motion unless an external force is acting on it. That's Newton's first law. And what is Newton's second law? The force is directly proportional to rate of change of momentum. That's Newton's second law. So for any frame of reference in which Newton's first law and second law holds good is called inertial frame of reference. The frame of reference subjected to inertia is an inertial frame. So what is inertia is? If the object is at rest, it is inertia. If it is moving with a uniform velocity, it is also inertia. The frame of reference subjected to inertia is an inertial frame. The frame of reference at rest or moving with uniform velocity along a straight line is an inertial frame. Now, this is the frame of reference. This frame of reference is at rest. It's not moving. This is the inertial frame of reference. And this is the another frame of reference. It is moving, but it is moving with a uniform velocity. Therefore, remember the frame of reference which is at rest, frame of reference which is moving with uniform velocity are inertial frame of reference. Now let us learn about non-inertial frame of references. Here, the frame of reference under acceleration is called non-inertial frame. Therefore, a coordinate system moving with either increasing or decreasing velocity along a straight line or under rotation is non-inertial frame. Here, in this frame of reference, this frame is moving with different velocity. That is, it's not moving with a uniform velocity. It may move with a increasing velocity or decreasing velocity. It's not moving with a uniform velocity. It's moving with different velocity, or it may accelerate or it may deaccelerate. And that frame of reference is called non-inertial frame. And if the frame of reference is rotating, and this frame is called as a non-inertial frame. Therefore, inertial frame means if the frame is at rest and if it is moving at uniform velocity, it is inertial frame. Non-inertial frame means it is moving with the acceleration or retardation. It's called non-inertial, and the frame of reference is under rotation with uniform angular velocity. It is a non-inertial frame of reference. Now let us learn about Newtonian relativity. Here, Newtonian principle of relativity is defined as absolute motion, which is the translation of a body from one absolute place to another absolute place, can never be detected. Translator motion can be perceived only in the form of motion relative to other material bodies. The fundamental physical laws and principles are identical in all inertial frames of reference. Now, let us learn about Galilean transformation equations. The transformation of coordinate of a particle from one inertial frame of reference to another frame of reference is called the Galilean transformation equations. Here, let us derive the expression for Galilean transformation. We have to take two frame of references. This Galilean transformation equation is very important to understand the special theory of relativity. Let's concentrate here. We have to take two frame of references. One frame of reference S, which is at rest, and another frame of reference S dash, which is moving the uniform velocity. Remember, at time t equals to 0, S and S dash are at the same position. Observer O and O dash are at the same point, or they coincide. At time t is equals to 0, observer S and S dash are at the same point. And as the time changes, the frame of reference S dash is moving, and also the particle is also moving. Here the frame of reference is moving with a uniform velocity, therefore it is a inertial frame of reference, and also the particle is moving with a uniform velocity. Then x, y, z is the position coordinate with respect to the observer. O, x dash, y dash, z dash, e dash is the coordinate with respect to the observer O dash, and P is the particle. Now, here I have mentioned S dash is moving with a uniform velocity and S is at rest. The observer O observing the event who is at rest. Another observer O dash who is moving with uniform velocity and also is observing the event T. Therefore, x, y, z, t is the coordinates with respect to observer O, x dash, y dash, z dash, t dash is the frame of this coordinate with respect to observer O dash. Now, according to the observer O, because the particle is moving along the x-axis, the distance of the particle P along the x-axis, according to the observer O, is x. Is the distance of the particle measured by the observer O, and here I have mentioned coordinate of P with respect to observer O is x, y, z, t. For distance OM is equals to x. Now, the position of the particle P with respect to observer O dash is x dash. Therefore, coordinate of P with respect to observer O dash is x dash, y dash, z dash, t dash is O dash m. That's equals to x dash. For the observer O, velocity of S dash is V equals to O dash by T, because the frame of reference is moving with the velocity V, is moving with a uniform velocity. Therefore, for the observer O, S dash is moving. It's moving with a uniform velocity and it displaces from O to O dash. Therefore, velocity is given by velocity is equals to its displacement O dash divided by time. Therefore, displacement O dash is Vt. Therefore, this distance O dash becomes Vt. So from the diagram, O dash m, this distance O dash m is equals to Om minus OO dash. Let us see here. O dash m is equals to OM minus OO dash. The O dash m is x dash here, OM is x, and O dash is Vt. Therefore, x dash equals to x minus Vt. And the particle is moving along the x-axis, it is not moving along the y, or it is not moving along the z-axis. Therefore, there is only a transformation along the x-axis. Therefore, the equation is x dash is equals to x minus vt, y dash equals to y, z dash equals to z, t dash equals to t. This is the Galilean transformation equation. If we write the inverse Galilean transformation equation, then the equation becomes x equals to x dash plus vt, y equals to y dash, z equals to z dash, and t equals to t dash. Here t is equals to tz because according to classical physics, the time is a absolute quantity. That is the event observed by the observer O and O dash are at the same instant of time. If the particle is moving in the space, then observer O and O dash observe that event. Here, remember, the velocity of the object is very small compared to the velocity of the light, and only t equals to t dash. Now, so this is the Galilean transformation equation. According to Galilean transformation equation, velocity is a variant quantity. So let us prove that velocity is variant under Galilean transformation. Here you have to take the frame of reference S and frame of reference S dash. S is at rest, S dash is moving with velocity V. Initially, S dash is at rest, but that time t equals to 0, both are at the same point. As the time changes, frame of reference S dash is moving, and the object, that is object, or this is the event which is also moving. Then This is the position of that particle P. The position of the moving object observed by the observer O and O dash are X and X dash. Already I have explained you in the previous slides. Now this is the position of the particle P from the observer O is X. Position of the particle from the observer O dash is X dash. Then, this is important. According to Galilean transformation equations, X dash equals to X minus Vt. Let's differentiate. Before going further, let us write the equation for the velocity here. Here, this is the displacement measured by the observer O. And what is the velocity here? Velocity is equals to rate of change of displacement with respect to time. This is the velocity measured by the observer O. And this is the velocity measured by the observer O dash. U dash equals to dx dash by dt. Here the displacement is x. Here displacement is x dash. Therefore, this is the velocity measured by O. This is the velocity measured by O dash. Now let us go to the Galilean transformation equation and differentiate it with respect to time. Then you get dx dash by dt is equals to dx by dt. V is constant because remember the uniform velocity V is a constant here minus V. Differentiation of t with respect to t is 1. Therefore, the equation becomes dx dash by dt is equals to dx by dt minus V. Here dx dash by dt is nothing but u dash dx by dt is u. Therefore, u dash equals to u minus v. Therefore, the velocity is variant quantity. So this is u dash equals to u minus v. The velocity for the observer O is u, but the velocity for the observer u dash is u dash equals to u minus v. Therefore, u dash and u are the velocities of the object with respect to O and O dash, and hence velocity is variant under Galilean transformation equation. And we prove that velocity is a variant quantity, but remember length, acceleration, force, Newton's law, conservation of kinetic energy, conservation of potential energy are invariant. Remember, invariant under Galilean transformation. In this video, we have learned about definition of space, time, event, observer. We also defined the inertial and non-inertial frames, Newtonian principle of relativity. We have derived the Galilean transformation equations and we learn which are the variance and invariance quantities under Galilean transformation equation. And the next session, we will discuss about ether hypothesis and Michelson-Morley experiment. These are the references. Refer these. Thanks for watching.